Alright guys, in the previous videos we've now covered off the basics of ACL injury. We talked about the mechanisms of injury and also some multi-planar loading mechanisms and potentially some strategies that might be able to abate that. So we're now ready to talk about prevention strategies in general. And we're going to start off about talking about the direct evidence that we have in this field. And what I mean by direct evidence is I'm talking about what's called prospective studies. And basically these particular studies, what they do is they perform some sort of intervention on a cohort of people. And then they also have a bunch of other people that serve as a control group. And they actually follow these people up over time to see how many of them suffered an ACL injury. And they basically compare the injury rate in the intervention group compared to the reference or control group. Now, this is direct evidence because you're directly assessing if a particular intervention is effective at reducing your risk of ACL injury. So this is basically our highest form of evidence, and it's really important that we first recognize that. Now, one issue with these sorts of studies is that ACL injury, in the grand scheme of things, their overall incidence is relatively low compared to some other injuries. Still high enough that they're a really important factor, but low enough that in order to study them, we actually need really big sample sizes. So we need lots of participants, or we need really long follow-up periods of time to observe enough ACL injuries that we can actually be confident in the ACL injury rates that we're estimating in the two groups. So that's one of the limitations of these sorts of studies. And one of the things that we can do, because all of these studies tend to be therefore quite small, is actually combine the results of all the different studies. And this is done via a process called meta-analysis. And meta-analysis is literally just combining the results of a bunch of different studies so that we can have more confidence in the conclusions. Because obviously, if each study only has a small amount of participants, if we combine the results from all the studies, then obviously our estimate of what's going on is we're going to be a lot more confident in that because we have a lot more participant numbers now in our calculation. So that's really what I'm going to show you here is the results of a meta-analysis that looked at all of those prospective studies where they've looked at the effect of having some sort of ACL injury prevention intervention compared to some sort of control. So the way I'm presenting this is in what's called a forest plot. So on the y-axis, you can basically see the different studies. And then along the x-axis, we have what's called the rate ratio. Now, basically, a rate ratio of 1, which is where you see that vertical dashed line, basically means that there was no difference in the rate of ACL injury in the intervention group compared to the control. Now, if the little square, so if you look along the plot for each study, there's a little white square. That square is basically what the rate ratio was in that particular study. And if that square is to the left of the vertical dashed line, that basically means that the intervention was effective at reducing the risk, or basically the intervention group had a lower rate of ACL injury compared to the control group. And if the square is on towards the right of that vertical dashed line, that basically means that the intervention group actually had a greater rate of ACL injury compared to the control group. Basically mean that the intervention was counterproductive, if that was the case. Now, for each of those little squares, you can actually see some error bars going out to the sides. They basically represent 95% confidence intervals. So basically, when those error bars cross that vertical dashed line, it means we can't be fully sure that the intervention was more or less effective than the control group. Okay? Now, what I really want you guys to focus on, obviously there's a little bit of variability from study to study, but if you look at the very bottom, it actually says combined, and then the square and its error bars are in green. So basically, this is through a statistical calculation. We actually pool the effects of all those different studies, and that green square and its error bars basically represents all the studies combined. Now, what you can see is that both the square and its error bars are to the left of that vertical dashed line, and that tells us that overall, these preventative strategies are effective at reducing your risk of ACL injury. Now, I don't expect you to understand the x-axis, the rate ratio, because it's on a log scale. That might be a little bit hard to understand what's going on. But in simple terms, basically what it's telling you is that if you perform these interventions you tend to see about a 50% reduction in the rate of ACL injury, which looks pretty substantial on the surface. But there are a few issues with this. The first is that the studies didn't all do the exact same intervention, so their protocols were actually quite heterogeneous and different. So it's really hard to know what specifically about those interventions is actually effective. The other thing to think about as well is the absolute incidence rates. So an absolute incidence rate would be like the rates that I explained in my very first video in this series, when it's expressed as something like 50 people per 100,000 tear their ACL or something like that. That would be an absolute incidence rate. Because the absolute incidence rates aren't massive, a 50% reduction in ACL injury rates also is not that massive. And I just wanted to point that out because a 50% reduction seems really, really big. But if not that many people are tearing their ACLs in these studies, it's actually not that much of a reduction. That's just something really important to keep in mind. Now, as I mentioned before, each of those protocols were somewhat heterogeneous, but they all fell under a branch of ACL injury preventative strategies called neuromuscular training. Now, I actually think this is kind of a dumb name for a type of training because I can't think of any physical training which does not involve the neuromuscular system, but for whatever reason, that's what they wanted to call it. Each of these studies actually have different components. So what I want to do in this slide is try and help you guys understand what's going on in each of those interventions. Obviously, I can't go through all of them in a lot of detail because each intervention is actually quite complicated. So this is just sort of a quick overview as to what's going on. So basically in this graph that I've put together, on the y-axis, you can see the different studies. Then along the x-axis, you have certain components that each study may have included. So you can see agility, balance, feedback, flexibility, plyometrics, and strength. So basically, if a study included something that targeted that particular attribute, it gets a green box, and if it doesn't have something that addresses that attribute, it's a red box. And what I've also done is I've organized the y-axis in terms of the effectiveness of the intervention. So the most effective intervention, as evidenced by its rate ratio, is at the top, and then the least effective interventions is at the bottom. And what you tend to notice first and foremost is that the top 4 interventions all included something that targeted all of those main attributes. So you've got one of your first take-home messages there that generally speaking, it's better to be more comprehensive than less comprehensive when it comes to ACL injury prevention protocols. Now, what that doesn't mean is that all of those components are really important because we don't actually know that for sure. So as an example, if you look at the Gilchrist study, which is the third from the bottom, it doesn't include a balance component, yet it seemed to be slightly more effective than the Stefan study, which is just below it, which did include a balance component. So even though it seems that the more comprehensive the program is, the more effective it is, we can't actually be sure which of those components are really, really important and which ones aren't important. So we don't actually know which ones we can take out or which ones we should focus on to make them better or anything like that. So that's something that's really important to keep in mind. Now, that was the direct evidence. So that's prospective studies, but we also have some indirect evidence. And this is basically where we have a decent biomechanical or theoretical framework to do something to reduce ACL injury risk, but we don't necessarily have any direct evidence showing that doing this particular intervention would actually reduce our ACL injury risk. So a good example would be strengthening certain muscle groups. So an example I'll go through here is the glute medius. I'll go through this relatively quickly, so feel free to just sort of go back through this slowly if you need to. But basically we have evidence that knee valgus is observed during injury scenarios, and then it says in vivo in brackets. In vivo just means in living, breathing humans. We also have evidence that knee valgus moments tend to load the ACL. This is in vitro data. In vitro just means like cadavers. We also have evidence that glute medius tends to oppose knee valgus loading, and this says in silico, that just means simulation. And then we also have prospective evidence suggests that participants with lower hip abductor strength tend to have greater risk of ACL injury. Now remember, prospective evidence is the real high quality evidence that we have the most confidence in. So if you combine all of those independent observations, what it tells you is that the glute medius tends to oppose knee valgus loading. Valgus loading is often associated with ACL loading and ACL injury. Therefore, if you increase glute medius strength, conceivably you could reduce your risk of ACL injury. Now, what's important is that we don't actually have any direct evidence that shows that strengthening the glute medius will actually reduce ACL injury rates. The other thing to keep in mind is that there's sometimes some inconsistency. So if you look at the very last box that I've got there, you notice the green is in a slightly different color to the other boxes. And that's just because there actually is some conflicting evidence. So I've also seen studies where hip abductor strength wasn't related to ACL injury risk. And that's something that's really important to keep in mind, is that a single study doesn't always have all the answers. Sometimes you need to look at a bunch of different studies. So that's something to keep in mind as well. Another important muscle that we talked about was the hamstrings. So we know that the hamstrings can unload the ACL. We know that reduced hamstring strength is associated with increased ACL loading. And we also know that hamstring strengthening is actually a really common component of IPPs. IPP just stands for Injury Prevention Protocol. And we also know that reduced hamstring strength has been shown prospectively to be associated with increased ACL injury risk. Again, that one's in a different color because I've also observed some conflicting evidence which shows no relationship between the two. But again, if you combine everything together, it looks pretty convincing, but we don't actually have any direct evidence that strengthening the hamstrings will reduce ACL injury rates. And that's a really important thing to recognize. And then the last muscle I'll talk about, as just a quick example, would be something like the soleus, because I've mentioned it before in this video series. So again, there's evidence that the soleus can unload the ACL, both in vitro and in silico. Obviously, there was my study which showed that the soleus induces posterior shear at the tibia, which would unload the ACL. But practically speaking, it would actually be really difficult to isolate the soleus from the gastroc if you were trying to strengthen it, for example. And that's actually a really important point because the gastroc actually tends to induce anterior shear at the tibia. So being able to target one and not the other is particularly important. I've also never seen any prospective evidence linking soleus strength or ankle plantar flexion strength, for example, to ACL injury. So obviously the evidence here is a lot more mixed. So if you're going to try and make an argument for targeting the soleus, you'd probably have to construct your argument fairly carefully. And in reality, you really should be considering the entire weight of the evidence, including the conflicting evidence. So maybe that means the soleus probably isn't that well supported. Now, as far as indirect evidence as well, we also have some biomechanical strategies. So here I'm going to talk about what's called the land softly technique, which basically means you increase your knee flexion angle during landing. So regular landing might go from this position when you first touch the ground to this position, whereas if you land softly, you'd start in the same sort of position, but you end in a much greater position of knee flexion. And the reason it's called land softly is usually the sound of your foot hitting the ground is a lot softer when you adopt this increased knee flexion angle during landing. Now, one of the reasons that it works is that it, or could conceivably work, is that it reduces your peak vertical ground reaction force. So here I've just got a general representation of the vertical ground reaction force. And based on the studies in this area, it tends to be lower if you land softly. Now, another thing to notice is that this vertical ground reaction force has a moment arm about the knee joint. And the moment arm tends to be slightly bigger in a regular landing, or we can call that like a stiff landing, compared to the soft landing. And the thing is, if you multiply that vertical ground reaction force by its moment arm, that will create what's called an external knee flexion moment. So this is the moment caused by the ground reaction force. And when I say moment, you could also think of that as a torque that's trying to flex your knee. So basically, if you land in that land softly technique, the external flexion moment will be lower because the vertical ground reaction force is lower and the moment arm of that vertical ground reaction force relative to the knee is also going to be smaller. So remember that a moment or a torque is equal to the force multiplied by the moment arm. So if the force and the moment arm are smaller, basically the overall torque or the joint moment is actually going to be smaller. Now this is really important because the external flexion moment, if that value is really big, that means your internal, so this is the extension moment produced by your body, needs to be really big. And knee extension is actually produced by your quadriceps. So if that needs to be really big, you need lots of quadriceps force. And remember, quadriceps tend to increase load on the ACL. So basically, in simple terms, having a smaller external flexion moment probably is a good thing because it'll tend to reduce ACL loading. Now, having an increased knee flexion will also alter your quadriceps and hamstring function. I'm going to explain that one in the next slide because I need some diagrams to help explain what's going on. But that's something to keep in mind. And then also based on some in silico studies, we know that landing softly tends to reduce your estimated ACL force. Now, there are some limitations with this. There's still no direct prospective evidence that landing softly will actually reduce your risk of ACL injury. The other thing to think about is how's this actually going to work in a real world scenario. So you imagine someone playing footy and they jump up for a mark and then there's all these players around them and then all of a sudden they're just supposed to magically land nice and softly. Well, it's probably not going to happen. So that's one of the things to think about when it comes to all of these interventions is how are they actually going to work in the real world. And the reality is we could teach someone how to land softly, but whether they're actually going to do it in a real world situation when they're at risk of injury, we don't really know that. Now, I'll jump back to that altered quad and hamstring function. So basically what I'm showing you here is the knee joint, and you can see the quadriceps and the hamstrings like I've shown you before. And I've picked 3 different knee flexion angles. On the left-hand side, you see anatomical position, so the knee's perfectly straight. In the middle, we have like a stiff landing. You could also think of that as like a normal landing if you want. And then on the right-hand side, you can see the knee flexion angle if you were in a soft landing position. Now, the first thing I want to focus on is the force vector of the hamstrings. Now, what you can see on the left-hand side, in anatomical position, the hamstrings actually don't have a big posterior shear force component when your knee is fully extended. But as you progressively flex more and more, so as you go to stiff landing and then soft landing, you can see that the line of action of the hamstrings relative to the tibia makes it more effective at inducing posterior shear force. So basically what that tells you is the more you flex your knee, the more effective your hamstrings are at pulling your tibia backwards. Now, if you look at the quadriceps force vector, this time, if you look at anatomical position, that's when the quadriceps tend to have their greatest anterior shear, whereas the more and more you flex, its ability to induce anterior shear becomes less and less. So in simple terms, the more and more you flex your knee, the less effective the quads are at inducing anterior shear and therefore loading your ACL. So basically, the more you flex your knee, your hamstrings become more effective at unloading your ACL, and your quadriceps become less effective at loading your ACL. So that's why it makes sense to actually adopt a soft landing sort of position when you flex your knee more and more. And in support of this, if you remember earlier to my injury mechanism section, we talked about how ACL injuries often occur when people land with their knee near full extension. And this is potentially one of the reasons why. Basically because the hamstrings are less effective at protecting the ACL and the quadriceps are actually more effective at loading the ACL. Now, there's also remember, it's not just about single leg landings. Another common mechanism we talked about was sidestep cutting. And sidestep cutting technique is the sort of thing that we've seen some evidence in this area, aiming to see if they can modify it. Now, in this case, they tend to focus a lot more on knee valgus loading because knee valgus loading tends to be quite high in sidestep cutting and is thought to be the important factor when it comes to ACL injuries through that particular mechanism. So basically a sidestep cut, we're really just focused on the stance phase, which would look something like this. But obviously I'm just going to focus just on the middle to early portion of the stance phase just to illustrate some of these factors. So basically there was a study of a lot of different participants and they looked at some of the factors, biomechanical factors, that were associated with lower knee valgus loading. One of the things that they noticed is that a lower contralateral trunk lean was associated with lower knee valgus loading. So to demonstrate that, I've got an example of a guy with a lot of contralateral trunk lean. And what's happening here is that the vertical ground reaction force, because of the way his body is configured, the vertical ground reaction force is actually just lateral to his knee joint, which means there's actually a little moment arm around the knee, which causes a knee valgus load. Now, if you reduce your contralateral trunk lean like this guy, basically the ground reaction force is going to point closer to the center of the knee joint. And as a consequence, that knee valgus moment is going to be a lot smaller. So that's why contralateral trunk lean is pretty important. Another thing that they found was lower cut width is also pretty important to reduce your knee valgus load. So a big cut width might look like this. And if you look at that vertical ground reaction force, it's really far away from the knee joint in the frontal plane, which means it's going to induce a pretty big valgus load. You also have the weight of your body weight pointing straight down. That also has a pretty big moment arm. And this time, because the force vector is in the opposite direction, it doesn't matter that it's on the other side of the knee, it actually still induces a knee valgus load. Now, if you reduce your cut width, for example, like the guy on the left, notice how that this vertical ground reaction force is a lot closer to the knee joint, so its moment arm's a lot smaller. So even though it still induces knee valgus, it's nowhere near as big as the wide cut. And if you look at where the body weight is concentrated, again, I mean, the body weight's exactly the same in both scenarios, but this time the body weight is a lot closer to that knee joint. So that means that because its moment arm is smaller, the overall valgus moment that it induces is going to be less as well. So that's why it makes sense to actually reduce your cut width. Reducing your knee valgus angle would also reduce your knee valgus loading. I guess that one's pretty intuitive. If you reduce your cutting angle, so what I mean by cutting angle is a really sharp cut might be if you're running forwards and then you turn completely 90 degrees. Whereas if you only cut by like 45 degrees, that would be a shallower cut angle. So basically the steeper your cutting angle, or the more you change direction, the greater the valgus loading. Another thing you can do is reduce your approach speed. So if you run up, before you do your cut, obviously you're going to run up to it. If you run slower, your valgus loading is going to be less. And another thing you can do is practice toe landing. So if you land with your heel, you'll typically see greater valgus loading, but if you land with your toes, you tend to see lower valgus loading. Now you'll notice that cutting angle and approach speed have a little asterisk next to them. And that's just because, again, in the real world, how's that really going to work? If you're playing some sort of sport and you're doing a sidestep cut, you're not judging the angle based on how much it's going to load your knee. You're judging the angle based on what your opposition is doing. So you can't really control that all that much in a real world situation. As far as approach speed is concerned, again, in the real world, when you're competing in sports, you have to move really, really fast. Reducing your approach speed probably isn't a viable strategy because it's going to compromise your performance too much. Now, if we talk about changing cutting technique, I guess the question arises is, are interventions actually effective in this regard? And we actually have some evidence behind this. So there was some work done by Dempsey back in 2009 where they did a 6-week targeted modification training and actually found that they were able to reduce contralateral trunk lean, reduce cut width, and all that eventually resulted in lower knee valgus loading. So potentially a short 6-week intervention might actually be effective at reducing your valgus loading. There are some limitations with this. They didn't actually quantify risk, so they didn't do the modification program, and then the ones that did it basically had a lower rate of ACL injury. That's not what they did in the study. All they did was they used knee valgus loading as a sort of a proxy marker for the general risk of injury. And again, you've got to ask yourself, is this actually going to work in a real world scenario? So you can train someone how to cut, but if you're assessing the effectiveness of your intervention as to how they move when they cut in a lab, well, you've got to consider that in the real world, you're going to have to deal with the ball going all over the place and, opponents running at you and yelling at you and telling you that they did things with your mum. And it's really hard for you to focus on the modifications that you've been taught in a completely controlled environment. So that's something to think about as well. These particular programs might be effective in a lab-based setting, but in the real world, we don't really know. There's also some evidence behind neuromuscular training, that we talked about before. Again, I think it's a stupid name, but there is some data where they looked at 2 particular interventions. These are relatively popular interventions when it comes to neuromuscular training. What's called the FMARC 11 Plus program and the Oslo Neuromuscular Warm-Up. You can obviously look those up if you're interested into what they actually do. But essentially they found that these interventions might actually reduce pre-landing quadriceps activity, which could conceivably reduce your ACL injury or your ACL loading. They also found that they may actually increase your pre-landing hamstring activity. Again, that might actually be a good thing because hamstrings tend to unload the ACL. They haven't found any convincing evidence that it reduces knee valgus loading. Generally speaking, they don't observe any differences before or after doing these interventions. There's even some evidence that it might actually increase knee valgus loading. So I guess that's something pretty important to consider. Again, these studies did not actually quantify risk, so they're not considered direct evidence. And again, real world scenario, who knows how this is actually going to work in the real world. And if we do the intervention properly, it might end up compromising performance. So that's something else that you need to think about when it comes to these sort of interventions.